functions in our function space X. And so the norm on E is going to be defined as the inf, and sometimes this will be X of E. This is simply the inf of the norms of all extensions. And so for this lecture, we're going to be extending functions exactly. Remember, yesterday there was a tolerance, and today, just for simplicity, we're not going to have a tolerance. We have a zero tolerance policy, but that's just for convenience in the lecture. Okay, here's more notation. Okay, Jx of f, the jet of f at x, is today the m-minus first order Taylor polynomial of f at x. I've written it down, or rather Polem has written it down. And so this jet Jx of f belongs to the vector space script P of all m-minus first degree real polynomials on Rn. Okay. All right, so remember x is Cm of Rn. That's there to remind us what m and n mean. And so constants that are denoted with the letters C, little c, big C, C prime, etc., always depend only on little m and little n. And there's the notation. A is dominated by B. That means A is less than one of these constants, C times B. And similarly, A and B have the same order of magnitude, denoted that way. If a constant times A is less than or equal to B is less than another constant times A. So things with the same order of magnitude can differ at most by a constant multiple, where the constants are determined by which space we're in. Okay, again, this is not, despite the fact that this is the heavy lifting part, it's not supposed to snow anybody. Am I right? All of this is perfectly clear. Okay. Please actually object if there's something to object to. Okay, now I want to recall the two theorems from the first talk. So now we have a finite set E in Rn, and it's a big finite set, capital N, some enormous finite number is the number of elements of E, and the claim is that we can compute the order of magnitude of the norm of f in X of E in, at most, n log n computer operations. So let me call that theorem the computation of the norm. Okay, so we can compute the order of magnitude of the norm quickly. The next theorem from last time is that we can efficiently compute an extension which is almost optimal in the sense given that, okay, that it agrees with the data and its norm is within a constant multiple of the inf of all possible such norms. And to compute efficiently means, remember, there's one-time work, query work, and storage. And the one-time work is n log n, the query work is log n, and the storage is n, and I'll call that the computation of the extension. And this is allegedly clearly optimal. Okay, so those were the two theorems from yesterday. Now, the proof was based on the construction of certain convex sets. I just want to remind you quickly of what the convex sets are. And again, this is not what they really are, but this is the pedagogical, simple version. And we don't worry in these expository talks about the difference between that and the real thing. So we have convex sets gamma sub L of xm, and they're defined by an induction. Here's the base case of the induction. Okay, when L equals 0, this gamma 0 consists of all polynomials that do that and that do that. And so that's the information that's what P had better do just based on information at the one point X, forgetting about all the other points in E and any information that may come from them. Okay? That's the base case of the induction. And then we continue, and here's the induction step. P belongs to gamma L plus 1 if and only if for every Y in E, there is a P prime in the gamma L of Ym, which we assume has already been defined by induction hypothesis. We already have the gamma L's. We're trying to build the gamma L plus 1s. So for all Y, there exists a P prime such that this inequality, which comes simply from Taylor's theorem, is satisfied. And so that was the inductive construction of the convex sets gamma L. Okay, and so last time, I guess there were three theorems. Theorem 3 from last time is that for a large enough integer constant L star, depending only on m and n, we find that if we look at any interpolation problem, all we have to do is look at the gamma L star, and if it's non-empty, that guarantees that we can make an extension whose norm is essentially M. So there's theorem 3, and the claim is theorem 3 is the heart of the matter. Well, in fact, it is, but there's more to it, and so I'd like to explain some new theorems. Or new, they're no longer new, but they're additional theorems, new, not contained in the talk yesterday. Okay, so the next theorem says that we can make the extension in a linear manner. So given, let's say, a large finite set in Rn, there is a linear map from x of e to x, so that, well, for any f in x of e, first of all, Tf equals f on e, so Tf is an extension of f, and furthermore, its norm in x is within a constant multiple of the least that it could be. So there's a linear extension operator. And in fact, this linear extension operator has a simple structure. It's a bounded depth. And let me just, let's look at the slide. We can take T to have a simple form. So for any x in Rn, Tf of x can be written like this with coefficients lambda xy independent of f. The fact that you can write that just reflects the fact that Tf of x is a linear functional on the finite dimensional vector space of functions on the finite set E. So of course you could write it as, as a linear combination of the coordinates. F of y are the coordinates of the vector f. So that's nothing. But the point is that the lambdas are sparse. For each fixed x, there will be at most a bounded number of non-zero coefficients. Okay, so the linear extension operator has this simple structure. So, okay. And moreover, T can be computed efficiently. And what that means is that we do one-time work, n log n, using storage at most n, and after that we can answer queries. And a query consists of a point x, actually not just in E, x in Rn. Okay, take any point x in Rn. The response to a query is simply the family of all the non-zero coefficients that enter into that formula. So not only is there a bounded depth operator, but it can be efficiently computed. Is it clear? Okay. All right. Now the next theorem is called a sharp finiteness theorem. Remember, finiteness principles are said to be a very, very essential part of this subject, but none has actually been stated. So here's a finiteness principle. So suppose I give you a set E in Rn, a finite set. Then there is a list, a not very long list of little subsets, S1 through Sk. So these are the little subsets of E, and there are not so many of them, so this number k is a big O of capital N. Okay, so there are only about as many of these sets as there are elements of E. And each one of these sets is very little. The number of points in this set is bounded for each one of these little sets. And these little sets can be used to calculate norms, because the norm of any given function from E to R, if we take any f, its norm here is of the same order of magnitude as the maximum of the norms of f viewed just on the little subsets S sub k. Okay. In one direction, this is obvious. This norm is obviously bigger than or equal to all of these, because it's harder to extend f from the whole set E than it is to extend f restricted to a subset. And back, right? That's a harder extension problem than that. So this is obviously bigger than this, but it's not much bigger. It's comparable to the max. Okay. So that's a sharp finiteness theorem. Moreover, these sets can be computed from E by an efficient algorithm using n log n work and linear storage. So that's the next theorem. So that's the sharp finiteness theorem. And please remember, if you have a little set S, then we can compute the order of magnitude of its trace norm just by linear algebra, thanks to the Whitney extension theorem for finite sets. And yesterday I said that but didn't get a chance to prove it. Please trust me, it's easy. Okay? All right. I hope you'll find the next theorem amusing. Removing outliers. Suppose we're doing an experiment to measure some function. We're experimentalists, and we measure lots of values, and so there are observations and uncertainties. Well, in today's lecture, the uncertainties are set to 0. That's just for simplicity today. But we measure lots of values. Unfortunately, every now and then, our machine is broken, and our experimental observation is bullshit. And so we ought to reject it. So we face the following problem. We're given a function on a large finite set, but we're also given an integer z between 0 and the size of the finite set. And what we would like to do is to find a subset S with at most z points in such a way that if you remove those outliers, because those were the days we think the machine was broken and our experimental results don't mean anything, okay, then we would like the norm of the resulting thing to be as smooth as possible. So we'd like the norm to be as small as possible. So imagine, for instance, there's some, let's say even for a function of one variable, you have some nice smooth curve, and you measure dots, and they're on the nice smooth curve, but 11 of these dots are just somewhere at random. If you try to fit all the dots, you can only do it with a function with an enormous norm. But if you remove 11 dots, they all lie on a nice curve, and you can fit with a small norm. That's what this is about. Okay? And so we want to find the set S that has at most z points and makes this norm as small as possible. Now, that's an extremely hard problem. I would bet that it's NP hard. If you can do that, you can do anything. I have no mathematics to support that. It's just a gut feeling that this is a very challenging problem. But the pleasant news is that an easier, watered-down version of this problem, which still carries a significant amount of the impact, is doable. So here's the easier problem. So I want to compute a set S star Z that wins an unfair competition. Here's the sense in which the competition is unfair. We wanted a set with at most z points, but we will get a set with at most c times z points. Let's say c is 20. So our c might be a lot bigger than 20 in practice, but let's say c is 20. So if we wanted z points, we'll wind up with 20 z points. This S star Z does a good job of competing against sets with at most z points. So that's a little unfair. We get to remove CZ points, and let's say God only gets to remove Z points. But nevertheless, God with omniscience does not defeat us by more than a factor of C, despite the fact that, well, okay. So in other words, our S star Z wins an unfair competition. It gets 20 times as many points as any competitor. And if these norms differ, I mean, if the competitor's norm is 20 times smaller than ours, we declare that we won. But nevertheless, our S star Z then has the feature that it is impossible to do much better with far fewer points, although it may be possible to do somewhat better with somewhat fewer points. That's the unfair competition. And the theorem is that we can compute an S star that wins the unfair competition in this many operations, C, Z, N log N, and storage Cn. This may not be optimal. I have no reason to believe this is optimal, but I was just very pleasantly surprised to see how this is relatively small. Okay? Furthermore, there is a structure in the problem. You can order the elements of E from the most meddlesome to the least meddlesome in such a way, will no one rid me of this meddlesome element? Let's see. So for any Z, S star Z has up to C times Z elements, and we simply pick the first C times Z in this order. So in other words, you might think that, let's say, if you were going to remove 10 outliers, you would remove 10 points. But if you were going to remove 53 outliers, you would remove 53 completely different points. No, no, no. It's possible to order the set in such a way that if you want to remove 10 outliers, you will pick the first 10. And if you want to remove 53, you will pick the first 53. So that's that theorem. Okay. Now, those are the theorems. So, oh, yes? Oh, because when I say 10 or 53, I mean C times Z. I'm speaking loosely. I absolutely do not solve the first question. Thank you for asking. So have I answered adequately? Oh dear. All right, that's bad. All right, wait a minute. Okay. So let me go back. What I mean here is that I can list the elements of E from the most meddlesome to the least meddlesome in such a way that for any particular Z, this set S star sub Z that I pick that is allowed to consist of C times Z points will be the first C times Z points with respect to this order. Okay, so I make that statement about the weakened version of the problem, but I make no statement at all about the original version of the problem. Okay, now am I right? It's completely clear. Okay, good. Okay, any other questions? Okay, if you counted, no reason why you should have counted, it seems there were 6 theorems stated so far. So now there are logical relations. And so here are the logical relations among the theorems. Let's see. So first of all, there was a theorem on the convex sets gamma. That's actually the heart of the matter, and that's what we're going to prove in the next lecture. Let's see. Once you believe that implies that there is a linear extension operator of bounded depth. It doesn't formally follow from the theorem, but it follows from the proof. The theorem on the convex sets gamma L says that there is an extension with a certain norm. And if you look at that construction, if you look at it a little bit carefully and add a little bit extra, you can make the extension that you construct depend linearly on the data. And if you look even more carefully and think how it depends linearly on the data, it's a linear extension operator of bounded depth. So the theorem on the convex sets will imply the theorem on the linear extension operator of bounded depth. Now, once we have the linear extension operator of bounded depth, there are 2 consequences of it. One is that we can make an efficient computation of an extension of a given function little f. That's obvious because we have constructed a linear extension operator of bounded depth. And once we've constructed it, if you give me a function little f, all I have to do is take my linear extension operator of bounded depth and apply it to the function little f, and that's my extension. Okay, so that's why we get this, and that's why that's obvious. Okay, but also the existence of a linear extension operator of bounded depth implies the sharp finiteness principle. That's not so obvious, but it is true, and we'll see in this lecture why it follows. And once you believe the sharp finiteness principle, then there are 2 consequences, namely the computation of the norm, which is allegedly obvious, and the algorithm on removing outliers. Okay? Now let's see. The computation of the norm is obvious from the sharp finiteness principle. Why? The sharp finiteness principle produced a nice list of little sets, and it said that the norm that we're interested in is comparable to the maximum of the norms for little extension problems. We know how to do the norm for a little extension problem using Whitney's extension theorem for finite sets. So therefore, once we have the sharp finiteness principle, we just apply it combined with our knowledge of little extension problems, and we win over here. How about removing outliers? That's not obvious, and if I remember correctly, that's the subject of the next few slides. But what I'd like to do in this lecture is explain all the non-obvious implications here, and then reduce matters to the theorem on convex sets gamma L, and then in the next lecture say something about the proof of that. Okay? And I have about half an hour left. Okay, so let's see how we're going to remove outliers thanks to the sharp finiteness theorem. Okay, well, let's just recall what we need to do that. So here's the sharp finiteness theorem. So the norm of f on in x of e is comparable to the max of a lot of norms of a lot of little problems. And the little problems are given by these subsets S1 to Sk. There are not so many of them. Each one is small. You can compute them efficiently. And for each k, thanks to the Whitney extension theorem for finite sets, you can compute this number yk, which is of the order of magnitude of the norm of the little extension problem. Okay? So that's what we're starting with, and we're going to use that to remove outliers. Okay? All right. So here's an algorithm. I'm going to present pseudocode for an algorithm called Outliers of EFZ. EFZ accepts as input our finite set E, a function f defined on the finite set E, and the number z, roughly speaking, the number of outliers we're supposed to discard. More precisely, we're supposed to discard c times z outliers, and we're competing against an omniscient competitor who, however, is only allowed to discard z outliers. Okay? All right, so here's the pseudocode. There. Okay, that's the input. Thank you. Oh, what does it do? It prints out the elements of the subset S star z that wins the unfair competition. So that's what the algorithm is supposed to do. Okay, now what is it? There's the pseudocode. So there is a loop that it executes. So there is the loop body in purple, okay? And it executes the loop body over and over again as long as the while condition is satisfied. So we look at the set E, and we look at the number z. Now, of course, if E is empty, there's not much we can do. We're extending functions from the empty set, and we're trying to remove outliers from the empty set. So there's nothing to do. We remove nothing from the empty set. There was nothing there anyway. And if z is 0, also, we're talking about removing 0 elements from the set E, and it's pretty clear how to do that. So we only do stuff while E is non-empty and S is not 0. All right, so as long as E is non-empty and S is not 0, we do stuff. What do we do? Well, first we compute our little sets S1 to Sk as in the sharp finiteness theorem. Now, for each of those little interpolation problems, we compute this yk, which is the order of magnitude of the norm of an extension. Okay? Now, one of these y's is the largest one. Well, maybe more than one is the largest, but we pick one particular k hat for which that y k hat is the maximum of all of these. Okay? And we pick that y k hat, and then we print out all the elements of sk hat, and they will be among the elements of our set S star z. Okay? So we print those out. Once we've printed those out, we then change EFZ by removing this set Sk hat. So we remove Sk hat from E. Of course, that changes F to the restriction of F to the new set E, which has the Sk hat removed. And we change Z to Z minus 1. And now we have a new EFZ. And we can now go back and look at this while condition and see whether it's satisfied. And we keep on executing the loop body as long as the while condition is satisfied. Okay? That's the algorithm. Now, I need to convince you that the algorithm does what it's supposed to. But before I do that, is it clear what the algorithm does? Any questions about what the algorithm does? Okay. I'm sorry? K. K is of the order of magnitude of the number of elements of E. Okay? And any other questions? Okay. All right, so let's see what it does. Well, first of all, all right, let S star Z be the set of all elements printed out by that. What do we have to show? We have to show that it contains at most CZ points, and furthermore, that it wins the unfair competition against any set S with at most z points. So there on the slide is what the thing is supposed to do. Okay. Now, the first bullet point, the fact that the number of points printed out is at most c times z is abundantly clear from the algorithm for the following reason. Each time we execute the loop body, we print out our set S k hat, and that had at most c elements in it. So we print out c elements each time, and then we decrease z by 1. By the time z reaches 0, we're done. We terminate the procedure. So, of course, we print out at most c times z points. Thank you, that was wonderful. Okay, the proof of the second bullet point is an induction on z. Okay, so the second bullet point is that we win the unfair competition. Well, let's work by induction on z. If z is 0, then of course we're printing out at most 0 points, and so the claim is that when we print out the empty set, we win a competition against some competitor who also prints out the empty set. So it's vacuously true. So let's now do the induction step. So let's fix a z, and let's assume the second bullet point for z minus 1, and we're going to prove it for z. All right? So, all right. So remember, here's the second bullet point. We have some competitor with at most z points, and here's what we have to show. Removing our s star z does, roughly speaking, does better than removing s, and there's this factor c, which makes the competition a little bit unfair. Okay, now what kind of competitors are there S? There are weak competitors and strong competitors. Okay, a weak competitor is a competitor with the property that if you remove S from the set E, that doesn't make the norm significantly less. That could happen, and in that case, it isn't a very smart thing to remove these guys because they're not helping. You should instead remove a small competitor, or I should say, God will remove a strong competitor because F, then the norm decreases significantly by virtue of removing the elements of S. So there are weak competitors and strong competitors. Okay? And I have to show you that this is true both for a weak competitor and for a strong competitor. Now, for a weak competitor, it's obvious that there's no problem because we look at what we remove, and we removed something, so obviously our norm is in fact less than or equal to, there doesn't even have to be a constant c here, this norm is less than or equal to this norm, and that's comparable to the norm of f in x of e minus s because s was a weak competitor. This statement, the fact that these guys are of the same order of magnitude, is what we mean by a weak competitor. So clearly, this guy is less than or equal to a constant times that guy. And so we've proven the second bullet point in the case of a weak competitor. Okay. Well, winning against a weak competitor isn't the problem. Winning against a strong competitor is the problem. So let's look at a strong competitor. All right. And now the point is that we should think about what happens the very first time we execute the loop body. So I wonder, should I zip back a little bit to the loop body so that we can see it, or do you remember it? What do you think? Shall we zip back? Let's zip back. There's the loop body. Okay, so think about what happens the very first time we execute the loop body. So remember, we compute our sets S1 to Sk as in the sharp finiteness theorem. We then look at the norms of each of the little extension problems, and we call them y1 through yk, and we pick the biggest one, and we print out the elements of it, and then we replace EFZ by something or other and continue. That's the loop body. Okay, now I'm going to go back to where we were before. Here's the strong competitor. Okay, so now remember what happens the first time we execute the loop body. We compute the S's, we compute the Y's, and we compute the K hats. And here these bullet points are the recalls. So remember here, the norm of F in X of E is comparable to the max of these guys. That's the sharp finiteness principle. Here, these norms are comparable to the YKs, and that's simply the defining property of the YKs, and we can compute them by, because we know how to do little problems. And then YK hat was defined this way. So those are the relevant points. And so what? Well, the crucial observation is that we don't know what our strong competitor is, but we are guaranteed that our strong competitor has at least one point in common with the set of points we decided to print out, sk hat. That's the crucial observation. So regarding this crucial observation, there are two questions. Why is it true, and so what? Let me answer why is it true. Okay? So, well, suppose this were not true. So then sk hat would be contained in E minus S. That means that, all right, now here's a chain of inequalities. Yk hat has the same order of magnitude of f in the space x of sk hat, and that's the defining property of the y. Now, sk hat is a subset of E minus S, so therefore solving an interpolation problem on an extension problem from sk hat is easier than solving an extension problem on the whole of E minus S, and so this inequality is obvious. Anything that agrees with f there also agrees with f there. That's where we use the assumption that this is false. Oh, there it is. Okay, so that's why this inequality is true. Now, S is a strong competitor, so by removing S, we have made this norm small compared to this norm. Okay? On the other hand, this norm, by the sharp finiteness principle, is comparable to the maximum of all these little guys. And by definition of the y's, the max of these little guys is comparable to the max of the y's. So this isn't equal, I guess this is only tilde, but this is of the same order of magnitude as yk hat. So look, yk hat is comparable to that, is less than or equal to that, is small compared to that, is comparable to that, is comparable to yk hat. That can't happen. That would say that yk hat is small compared to itself. I guess yk hat could be 0, but let's assume that we're not trying to, let's assume the function from which we're trying to remove outliers is not the 0 function. So we get a contradiction, and so therefore this property is true. Okay, so now it's easy to decide the second bullet point by using the induction assumption. So let's think what happens now. We have printed out sk hat, and let's say our opponent has printed out one point of S, namely the one that belongs to sk hat. Okay? And now we and our competitor are in the same relative position as before, except that our set E has fewer points. Z has been replaced by Z minus 1 because our competitor has used up one of his Z points and we have used up C of our CZ points. Everything is the same, but with Z replaced by Z minus 1. And therefore, by the induction hypothesis, we win. I have that written down in a little bit more detail, but I'm just going to do that. Yes, so this completes the proof that, of the second bullet point, and it shows that the algorithm performs as promised. And if, I haven't said how many operations or how much storage it uses, but it's perfectly easy to go back and check what I said. So that's how the sharp finiteness theorem implies that one can remove outliers. Let's see how much time I have. 15 minutes. Okay. Yes?
How do you know your outlier algorithm doesn't capture all of these?
Oh, it might. It might. There is the question of what this number z is. So let's say if I'm supposed to remove 1% of the points of E, then my algorithm will be useless because it might easily tell me to remove all of E. But if Z is small compared to E, then I can remove at most CZ points. And so if CZ is, if I have 50 billion points and I'm allowed to remove 100 of them, and C is 100, then I'm removing at most 10,000 points out of my 50 billion. But you're absolutely right. If Z is of the same order of magnitude of E, then this theorem tells you nothing. Okay? Okay. Well, let's hope let's hope that our experiments are so good that most of our results are meaningful. Okay. All right. All right. Now I'm going to switch completely, and I'm going to show you the other non-trivial logical implication, how one theorem yields another. Namely, I'd like to explain how if you know that there is a linear extension operator of bounded depth, then you know that there is a sharp finiteness theorem. Okay. Now, the plan to do that is to use the well-separated pairs decomposition and use the linear extension operator of bounded depth. And so first there's going to be a discussion of what comes out of the well-separated pairs decomposition for this problem, and then what comes out of the linear extension operators of bounded depth. We will get two lemmas. We will then put these two lemmas together and produce the sharp finiteness theorem. Okay? All right. As a warm-up exercise, I would like to go back and prove that the Lipschitz constant of a function on a finite set can be calculated the way I said in the first lecture. Now remember, I promised it could be done with a 1% error, but by virtue of my being too tired when I produced the handwritten slides, what you'll see here is that there will be a computation up to a factor of 100. But that's just because I was sloppy in writing the slides. The exact same idea yields the Lipschitz constant to within a 1% error. So remember how the well-separated pairs decomposition works. Well, remember what it is. We're given a large finite set E in Rn, and we look at E cross E minus the diagonal and partition it into Cartesian products. The number of Cartesian products is big O of the size of the set E, and yet each of these Cartesian products is well separated in the sense of this last line, that the diameter of this guy plus the diameter of that guy is at most 1/1000th of the distance between the two star clusters. That's the well-separated pairs decomposition. Okay? Now, for each of these Cartesian products, we pick one single representative. We pick one point, x nu prime, x nu double prime, in the Cartesian product. Okay? And the thing that I owe you from talk 1 is that the Lipschitz constant for this function defined on the set E differs at most by a factor of 100. And again, this shouldn't be 100. This should be 1.01, and the proof that I'm going to give you works for that. But all right, let's say differs at most by a factor of 100 from the maximum of the difference quotients that you compute just from the representatives. Okay? So as a warm-up exercise, I would like to prove that for you. Okay. Well, I'm going to prove it by contradiction. So here's our hypothesis. Let's say this Lipschitz constant that we get this way is 1. Then I've got to show that this Lipschitz constant is at most 100. Okay? So if for the representatives we have a Lipschitz constant 1, then for the whole set E we'll have a Lipschitz constant at most 100. Let's prove that. Okay, suppose that's false. Well, then there's a counterexample. Whoops, and I'm sorry. So x and y here, I guess, should be x prime and x double prime. So f of x prime minus f of x double prime, let's say, will be strictly bigger than 100 times the distance from x prime to x double prime. And we'll do that with this distance from x prime to x double prime as small as possible. And there's no problem about picking the minimal counterexample because this set E is finite. If there is a counterexample, there are finitely many counterexamples, and we pick the one for which this number is the minimum. Okay, so because it's the minimum, if there are any 2 points, x and y, that are strictly closer than that, then we have the desired inequality. Okay, so I'm going to call that inductive hypothesis. This proof is by induction on the distance between the 2 points, and so this is like an inductive hypothesis. Any 2 points that are closer together than these two satisfy the desired inequality, and I'm going to prove to you that, in fact, these two also satisfy the desired inequality. Okay? All right. Well, notice that our minimal counterexample lies in E cross E minus the diagonal. That is, x prime is not equal to x double prime. And that's simply because we have a counterexample with a strict inequality here. If x prime and x double prime were equal, there would be an equality 0 equals 0. So x prime and x double prime are distinct. And because they're distinct, they lie in one of these Cartesian products. So now let's fix anew such that x prime, x double prime lies in the Cartesian product. Well, but the representative also lies in the Cartesian product, and the Cartesian product is well separated. So notice x prime and x prime nu lie in this star cluster. X double prime and x double prime nu lie in this star cluster, and these two star clusters are well separated. Consequently, if you look at x prime minus x prime nu plus x double prime minus x double prime nu, that's less than or equal to 10 to the minus third times this guy, because this is at most the diameter of one star cluster, this is at most the diameter of the other star cluster, and this is at least the distance between the two star clusters. Similarly down here, I don't think we're going to use this one. Well, I don't remember. We use one of these two, but not the other. I forget which. Okay? So anyway, that's true. Now, in particular, x prime minus x nu prime and x double prime minus x nu double prime are strictly less than the distance of the minimum counterexample, the minimal counterexample. Therefore, by inductive hypothesis, f of x prime and f of x nu prime are related like this with a Lipschitz constant at most 100, and similarly for the double primes. So that's simply because, right, for anything with smaller distance, we don't have a counterexample. All right, so we know that. So now let's gather what we know. We know that. Okay, we just saw that. We know that, we just saw it. And we know that these two guys are representatives, and by definition, by assumption, these two representatives satisfy a Lipschitz estimate with a constant 1. Okay, so let's just combine all these guys with the triangle inequality. And so the distance between f of x prime and f of x double prime is less than or equal to 100 times this guy, plus 100 times that guy, plus that, just the sum of the right-hand sides. Now, all right, let's see. Okay. Notice here what has happened here. I've replaced x nu prime by x prime and x nu double prime by x double prime. And so when I use the triangle inequality, I have an extra 1 times this guy plus 1 times that guy. So these hundreds become 101s. Okay, so that's where this line comes from. Okay, is it clear? We're almost done. Okay, so now I've just recopied the last line. We know that. But we also know that these two guys are less than or equal to 10 to the minus 3 times that. And so, therefore, f of x prime minus f of x double prime is less than or equal to, let's see, that's 101 times 10 to the minus 3, and another 101 times 10 to the minus 3, and 1. That's less than or equal to 2. Okay, so f of x prime minus f of x double prime is less than or equal to 2 times x absolute x prime minus x double prime. But wait a minute, x prime minus x double prime was assumed to be a counterexample, so this guy is supposed to be strictly greater than 100 times this guy, and yet it's less than or equal to 2 times that. That contradicts the assumption. So we've assumed that the desired inequality is wrong, and we've gotten a contradiction, and that's it. Okay, how much time do I have? 5 minutes. Okay, so that's the warm-up exercise. Now, let's go back to the sharp finiteness theorem, coming from linear extension operators of bounded depth. In the same spirit as the warm-up exercise, we can prove the following lemma on Whitney fields. It is the glorified warm-up exercise, proven by the exact same idea. Suppose we have a finite set, a well-separated pairs decompositions, representatives, etc., but now instead of a function, we have a Whitney field, a p arrow. And suppose that capital M is some positive number. Okay? Well, suppose that this condition, which we remember from the Whitney extension theorem, suppose that this condition holds, but not for all pairs of points from E, but only for the representatives. Then, whoops, there should be a constant here. So it's not the same M, but C times M. And this implication follows for all xy in E and for all alpha. And it's just the same idea. Okay, if it's not true, there's a minimal counterexample, but then blah, blah, blah. Okay. All right, now we've got to bring in extension operators of bounded depth, and I have 4 minutes. So suppose that T is a linear extension operator of bounded depth. So given a set X in Rn, the jet of TF at X is computed from not all of F, but only F at a few points. Let's say the restriction of F to the set S of X, where S of X is a subset of E with at most C points. That's what it means for the operator to have bounded depth. Okay. Okay. Now we know that TF equals F on E, and that TF does a good job of extending. That's the inequality at the bottom of the slide. Okay. And so now, now there's a lemma that I'm not going to have time to prove, but it's the following. Well, oh, you know what? Never mind. Let's ignore the statement of the lemma. The point is, all right. Here's the point. What are our sets? Remember, the lecture's almost over. The proof is now going to be fudged, fuzzed, whatever. One idea from the proof. We're supposed to produce, for the sharp finiteness theorem, we're supposed to produce a short list of little sets. What are they? Where do these sets come from? I'm not going to check that they work. I have 2 minutes left, but I will explain what these sets are. So given the set E, we have our well-separated pairs decomposition, and we have a list of representatives. Each representative consists of 2 points, this one and that one. If you want to compute the linear extension operator, the value of the linear extension operator at this, or let's say the jet of the linear extension operator at this point, is determined by a few of these points out here. Similarly, the jet of the linear extension operator applied to F at this point is determined by the values of F at a few of these points out here. Okay? For each pair of representatives, I take these points, and then maybe also these two. That's a set consisting of a few points. And for each representative, for each pair of representatives from the well-separated pairs decomposition, I do that. That's a short list of little sets, and it has the desired properties thanks to the glorified warm-up exercise and the lemma that I didn't have a chance even to state carefully, let alone to prove. But I think that is the end of the discussion of that implication, and that in principle reduces everything to the lemma on these, to the theorem on these convex sets gamma, which will be the subject of discussion of the next lecture. Thanks. Of the next lecture, not the next lecture. Thanks. I think that the answer is no. I'm not sure. Let's see. So for instance, suppose that all this, let's say we're in the plane and all the points except very few of them lie on the x-axis. If you want any information about y derivatives, you had better bring in the few points not. But that's not a proof, and I could be wrong. It would, of course, be very interesting to, if I am wrong and if it is possible to pick the sets as you suggest, I think that would be very interesting. Any other questions?